Hello and welcome to episode 2 of Astromagnet. I'm Arush Ramadurai,
I'm Ishan Chakravarti.
and today we're talking to Dr. Joseph Lazio, Directorate Scientist of the Interplanetary Network Directorate at the Jet Propulsion Laboratory.
Welcome to the podcast, Dr. Lazio. When did you first get interested in astronomy and astrophysics? What about it interests you?
That's actually a tough question for me. I've always been interested in science. I went through a phase of really liking dinosaurs. I distinctly remember sneaking out of my bedroom window, and it was next to our garage in that house, and just sitting out and looking at the stars. So somewhere along the line, I got really interested in space, astronomy, stars, and never kind of left me. And I got to grow up and actually do what I wanted to do as a boy.
So can you talk a little bit about the trajectory of your career? Like what kind of education did you get that prepared you for it?
Yes, and it's not been exactly a linear trajectory. I got an undergraduate degree at the University of Iowa in physics, and I recommend highly, physics or math. If you can do something like that, you can do almost anything. After the University of Iowa, I went to Cornell University, where I got a PhD in astronomy, and that's a fairly common to do research one, and that was always the career I wanted to take was to do research in astronomy and astrophysics. You need a PhD. After the PhD, I went to the Naval Research Lab as a postdoctoral researcher or postdoctoral scholar. You can think of that as almost an apprenticeship. That even in graduate school, even after a PhD, you don't really have all the skills that are needed to go become a faculty member. So I did a couple years, almost a year and a half actually, of a so-called postdoctoral research. And I just happened to be at the Naval Research Lab at the right time. They were starting up a new program. It was exactly in one of the areas where I had some good skills. And I transitioned from being a postdoctoral scholar to a staff member at the Naval Research Lab, which was actually really, really cool in a couple of respects. One of them was when I was growing up, I read a lot about radio astronomy, and my title at the Naval Research Lab was radio astronomer. So I could actually say, I wanted to be a radio astronomer when I grow up, and I am one. And then about 10 years ago, I got an offer to move to the Jet Propulsion Laboratory. It was not an offer I was expecting. It was not an offer that I was not intentionally trying to work for NASA, and actually, that I didn't say the Naval Research Lab is in Washington, D.C., so it's on the east coast of the country. And having grown up in Iowa and spent a lot of time on the East Coast, actually moving to Los Angeles or moving to the Southern California area was one of the challenges of my wife and I of, can we actually live in Southern California? Of course, now that we're here, we love it. But at the time, it wasn't so much the job. It was, can we actually survive in Southern California? Because it's this foreign country compared to what we're accustomed to. But it turned out very, very well.
So what were some of the favorite courses or research experiences you had as kind of a young physicist?
Yeah, that's certainly anybody thinking about going on, certainly to a career in research. Look, and if you're thinking about universities or colleges, try to figure out ways to get involved in research. I got involved in research very early through a program that the University of Iowa was actually kind of just starting up at the time. As a result of that, I got to travel to the Very Large Array in New Mexico, and then to the Arecibo Observatory, all while I was an undergraduate. And in fact, one can, these days, there are many more such programs, but it was just actually being able to do research, getting to know some of the graduate students at the university. That was certainly one of the highlights that I look back on, say, my undergraduate university experience, and that was really great. The favorite courses, the other part about that is you have to take physics and math, of course. or some aspects of engineering perhaps. But knowing about other parts of life are important. So I remember having some literature courses. I still, some of the literature courses I took were fantastic. And being able to read and write the English language is incredibly important. For whatever reason, the English language is the lingua franca of science. So being able to read and write it, and I make all kinds of presentations, I write papers, being able to read and write and speak English language is incredibly important for communicating ideas. So taking the physics and math is crucial, but don't neglect the other things as well.
Sounds like really helpful advice. Could you talk about some of the projects you've worked on, like the Dark Ages Radio Explorer and the Square Kilometer Array? And why do you feel these projects are needed to further our understanding of space?
That's a big ask. Let's see. Dark Ages Radio Explorer was a concept to look at the universe actually when the first stars were just forming. Stars form out of hydrogen. Hydrogen is the most abundant element, and the Dark Ages Radio Explorer, or DARE, was a concept to put a single radio antenna in space and try to detect the radio emission from the hydrogen atoms out of which the first stars are forming. That has turned out to be an incredibly difficult problem, far more difficult than I think we appreciated when the concept was first dreamed up. So at the moment, all of the focus on that is doing it from the ground, because we have to be able to do it from the ground before we can do it from space. It's just so difficult to get into space. The Square Kilometer Array, I mentioned the Very Large Array, which is in New Mexico. Even 30 years ago now, people were thinking about what is the next big telescope, because essentially all telescopes are just light buckets. The universe is really, really faint. And so we need to build bigger telescopes in order to study the things we understand better, as well as discover new things. And the Square Kilometer Array, as the name suggests, it is an effort to build a telescope that has essentially 1 billion square meters, or a square kilometer worth of metal that is used to collect radio waves, and again, driven very much by how faint the universe is at radio wavelengths. And that was a fantastic experience. I got to travel the world talking about radio astronomy and meet with colleagues, come up with new projects. I still look back these Square Kilometer Array days, although the telescope isn't built yet, trying to figure out how to build it and what is the science case. Why should we build it? That was a lot of fun and really rewarding.
Can you tell us some more about what radio astronomy is and why it's important to astronomy as a whole?
Sure. Everybody's all familiar with the colors of light that we see. So what I often say is there's a whole spectrum of colors, not all of which we can see. So let's take some common examples. The spectrum is red, orange, yellow, green, blue, purple, or violet. So what happens if you get a color that is more violet than violet? Well, that's what we call ultraviolet. And that's, many of us may have had an experience of getting a sunburn. If you keep going to shorter and shorter wavelengths, you get to X-rays. And many of you, maybe you've had an experience of getting an dental or bone, and you keep going to even shorter wavelengths, you get to gamma rays. If you go the other way, so you go to a color that's more red than red, we get infrared, which is often what we feel is heat. And if you keep going, you get to microwave and radio. So there's this whole spectrum of colors, only a small fraction of which our eyes can see. And if you imagine, suppose the only color you could see was yellow, the universe would look a lot different as opposed to somebody who could see the whole spectrum, right? If you could see red, orange, yellow, green, blue, and violet, there's a dramatic difference between somebody who could see only the color yellow. So by restricting our view just to these little colors that our eyes can see, we're missing a whole bunch of the universe. And there have been, it's probably a completely another hour to describe it, but many of the things that we consider today modern astronomy, people first discovered them at radio wavelengths because it was a new way of looking at the universe. So we use radio wavelengths and gamma rays and infrared and ultraviolet because then we both find things we wouldn't see otherwise, as well as get a much better understanding of the sources in the universe.
So what sorts of sources are you looking at that are, if you look at them with radio, you get a lot more or a lot different information than if you were to look at them with ultraviolet or infrared? I guess I'm asking, for which sources is radio astronomy most suited, and, what are you looking at nowadays?
There are two answers to that. Actually, what am I looking at these days? Well, one very simple one is last week, I actually participated in a meeting in which NASA approved us to move forward with putting a small radio telescope in space. And what it will do is view the sun. It will look at the sun. Actually, it will look at eruptions that the sun produces. And this is a perfect example. So when the sun erupts, and these are sometimes called coronal, both flares or coronal mass ejections. What happens is the sun, by processes we don't quite understand, we don't quite know how the sun does this, but it's able to accelerate subatomic particles, think protons and electrons, to energies that are substantial. They're substantial enough that, for instance, if one of these protons hits a spacecraft, it can damage it. If you're an astronaut and you have enough exposure to these energetic protons, you can actually get radiation sickness. Those protons, and particularly actually more the electrons do not actually radiate that well at say ultraviolet or at the wavelengths our eyes see. They radiate copiously at radio wavelengths. So we're going to be putting this radio telescope in space to watch the sun and watch the radio emission that is generated when these explosions happen. And the science, the underlying physics question we're trying to answer is, how does the sun manage to generate these energetic particles? And the radio telescope will help us. One of the things we just don't even understand today is, where are those particles being generated relative to the sun? So just figuring out where the particles start relative to the sun will help us with the physics. One of the other projects I'm sort of doing, I'm doing actually in conjunction with an undergraduate student. She's done a lot of work on it. She's done a lot more than me, actually. I took some data using a different radio telescope, and we are trying to figure out if we see two supermassive black holes in orbit about each other, or actually the radio emission that results when material falls into supermassive black holes. Do we see two that are orbiting each other? And that project is still ongoing, but it's kind of taking me back to my roots. So it's something I'm spending a lot of time thinking about, and I really like it.
So what are some of the different phenomena you've studied over the years, like black holes and the sun's eruptions?
Right, those are two. But I've spent a lot of time working in one way or another with pulsars. Pulsars are, I see both of you shaking your heads, but pulsars are neutron stars, which means that they're about 10 kilometers, 12 kilometers in radius, but they contain about 50% more mass than the sun. They tend to rotate rapidly, a second, in some cases, say 100 times a second. And they typically have very strong magnetic fields. So this combination of rotation and a magnetic field, I will gloss over some of the details, but they generate radio emission. And if they rotate in a way that the radio emission points toward us, we get a pulse, hence the name pulsar. Those can essentially be used as clocks. So I've been involved in multiple projects in which we look at some aspect of how the pulses from the pulsar are traveling to the Earth, or essentially using the pulsars as a clock, and then studying some other aspect of physics. Yeah, why don't I've been involved in lots of things. I often say that I love all radio waves. So I've been involved in everything from trying to find radio emission around from disk of material in which planets might be forming, to pulsars, to finding finding a pair of supermassive black holes. Yeah, lots of things.
Do you have a favorite thing you'd like to study out of all of those?
It's, in fact, people, well, I've not been involved in those projects because they were sort of earlier than they were happening when I was still in graduate school. People have actually flown, and the Japanese and the Russians have flown an antenna, and the radio astronomers of the world collaborated to form a radio telescope that's in fact bigger than the Earth in a couple of cases.
Is it okay if interested high school students contacted you for advice and guidance by email?
I'm going to try turning on the video again. The answer is yes, Alibite. As I said, I'm overcommitted, so I may not be able to respond immediately.
Right.
And at some level, if my career trajectory certainly was not linear, I think I've provided some of the key advice of get a good degree in physics or mathematics, something like that. Mm-hmm. That will carry you far. And yeah, so some of them, I can't forecast the future any better than anybody else. So that's the kind of advice I give typically.
It's really good advice. Thank you for your time. So that was Joseph Foster. To learn more about his field, check out our website for additional resources.
Thank you, and we'll be back with another episode soon.